is just to differentiate. And here I'm centering at 0, right? Which is bad because this is a singular point at 0. I can't do this. See, this is the thing I shouldn't do, right? Because what is x equals to 0 here? Right? To put it in the better Drake format. That has a clear singularity at x equal to 0, which is the one point that I should not write a power series solution at. In fact, go back to the start of this lecture. What were we doing? I was essentially putting x to the r as the solution, right? Which is a kind of stupid power series. Or is it? And what happened? We plugged it into the differential equation, which had a singular point of 0, and yet that somehow worked, right? But if you look at what we did we really have a power series solution at the start of this lecture? Is 1 over x cubed something that a power series can have as a term? No. Power series have things like 1 and x squared and x cubed. And I didn't do it, but it would have been easy to get r being a fraction. We could have square root of x, x to the 3/2, x to the 7/5. All of those things are possible in the Cauchy Euler problem. Because the Cauchy Euler problem is not something that is a solution at a non-singular point. So calling a point which is not singular a non-singular point gets kind of old. What would be a better name for a point which is not singular? It's the kind of point we usually solve a differential equation at, so it is called an ordinary point. So I've chose the one point which is not ordinary to try to start this example, and it won't work because of that. And that's fine, because we didn't have time to really finish it, even if I had done it better. So this is what we're going to be doing next time, is like showing you how you can write down a power series solution and plug it in, and then work out how the coefficients have to be related. It's actually pretty straightforward. Of all the things we've done, it really requires the least memorization. It's just gory calculation, really. But you guys usually do pretty well at this. It's the remembering how to find power series representations of functions that you didn't learn in Calculus 2 that hurts you more. So I'll put that on the quiz to try to refresh your memory some, but anyway. So we have a few minutes left. I thought I would leave the last 10, 12 minutes for questions about the test. And also, before I forget, I do have your quiz. Quiz 1. Sorry for the delay on this, Grace. Quiz 2, it has not finished yet. But I am told I should have it to turn back to you guys in office hours tomorrow. So hopefully that's actually the case. I think it will be. He sounded pretty sure about it. We'll see. So my office hours tomorrow morning, about 9 till what? Oh,
my name's not John.
I know you're not John. What's wrong with me? Goodness gracious, John, I don't like the way he reacted to being called your name. How do you feel about that? I don't know. Josh. Back to Josh, thanks. Other Joshua. Well, all right. No, Ripken. Let's see here. I love your last name. It gives me joy. And let's see here. Joseph. Kelly? Okay. Robert, where is Robert? No Robert? Anybody see Robert today? Malate? Caleb. Oh, you're right in front of me. There you go. Jake? Is there a Jake? No Jake. All right. Oh, sorry. My bad. Claire? Everybody who turned in quiz 1, I think I gave everybody one, right? Uh, 8:55 till 10:30, I think. Now, if you guys don't have any objection, I will leave them on a chair outside my office if I have to leave, so you can get them later. Yeah. So what would you guys want to look at? Anything in particular? Quiz 1? Anything quiz 1? I mean, we could look at quiz 1. We could look at an old test, whatever you'd like. Old test, all right. Sure. Pick a year, any year.
Last year. This year. In the future.
Let's see here. With or without, let's with or without solution. Probably with solution you'd like. All right. Now, is problem 11 on your test? No, it is not. All right, let's take a walk down memory lane here. Oh.
Stop.
It's fine. Aw, man. Oh. Stink. My new lasers are in my backpack. My new lasers are so much more awesome than this one. Well. Okay, so problem 1, find the explicit solution. So what's that mean? When you see explicit solution, that means you have to solve for y, right? In this first one, you're given also that y of 1 is minus 2, right? And so, you know, I think 40% of the class left plus minus in their solution. This is wrong. You must make a choice, right? You have to choose the minus because we have y of 1 is minus 2. If I plug in 1, I get log of 1 squared. Log of 1 is 0. Square root of 4 is 2. In order to get minus 2, I must have a minus there. I cannot put plus minus there because that is unfinished, right? Plus minus in the general solution would be fine, but this is not that. Questions? So when I put a problem on your test that there's a plus minus, then you have to choose either the plus or the minus. You're going to think through it and not give me this story to tell for next year's differential equations, right? Okay. You ever seen that? Remember that scene from The Force Awakens where they, with the mirror and it goes on and on? It's kind of like that. Or is that The Last Jedi? It's The Last Jedi, I think. I don't know, so forgettable. Yeah. You're like, you'd ask something that easy? Yeah, I might. It's very possible. I do want you to be able to do this. How long should it take you to do this problem too? Yeah, a minute. You should, a minute, 30 seconds. These are reasonable numbers to give. I mean, do it carefully. You should be careful though. I mean, don't hurry too much in the sense that if you do if you factor it wrong, if you looked at this and somehow were like, d plus 1 times d plus 9 or something like that. I don't know. It's hard for me to give wrong ways to do things, but if you somehow found a way to do the algebra wrong here, you can mess it up. That's even more true for this kind of problem. Now, notice the dd theta. So I had students who wrote an x here and a theta, like they had, they put like an x here or a theta here, or some had like x's here and t's here. Some had just the thetas like they're supposed to. I mean, there's a variety of ways students find a way to get that wrong. Find the integral curve of the vector field through 1, 2. I was looking at this a different way last year, so you can take it or leave it my way of thinking about it here. I like the way we thought about it this year more, so I don't want to say much about that. I mean, because this year we learned that, what was the way I looked at it this year? It's a little bit more direct. This year, the way that I have packaged this thinking is we're trying to find dr dt equal to like p of r of t, q of r of t. So really, and this is dx dt, dy dt, yeah? So if you look at it, we're really just trying to solve dx dt equals to p and dy dt equals to q. And we've actually solved some of those. At the first day, we solved these. A couple of them, at least one of them. And I pointed out to you that we could also look at this as dy dx, and taking a clue from chapter, calculus 1 rather, we can look at this as the quotient of the parametric derivatives. And so we're really just trying to solve dy dx equals to what? Q over p, yeah? So to find the integral curves to a vector field p comma q, we can just solve the differential equation dy dx equals to q over p. That was a pretty efficient and nice way to look at it. I have to be really careful. This over here, it's a little bit more dangerous for me to ask you to these. I have to be really careful asking you to solve these kinds of systems because there's really only a select subclass of those that you currently have the technology to do, to hack through these problems. Pretty much they'd have to be uncoupled or look almost exactly like what we did in class. Although if you go back and look at what we did there, it probably makes more sense now because at the time I had to just ask you guys what's the solution to y prime prime plus y equals to 0. And one of the I think somebody in the peanut gallery in the back there, which one of you want to use, said cosine. Yeah, it was, okay. Thank you for that. So, but in retrospect, I mean, that was a good guess, but now that's not just a guess. We have ownership, right? Somebody asks you, what's the solution for y prime prime plus y equals to 0? You're just like, oh, that's lambda squared plus 1 equals to 0, which is lambda equals to plus or minus I. So that either means cosine t or sine t if I'm working in y prime is dy dt, right? Like that's not a guess anymore. That's part of an informed, it's an educated guess. Okay. Anyway. Problem 5 is Bernoulli. And as I have told you guys in class, if I ask you a substitution problem, I will also tell you, make the substitution whatever it is, right? That's not right. I should probably substitute the right spelling there. Ooh, multiple choice. Who'd thunk it? Yes. They may or may not be. If you don't mind, I can post it in course content for you. That'd be good. So I'll do that. So here's, an easy way for me to test the annihilator method is by multiple choice. It's a nice way for me to see whether or not you know what you're doing without banging my head against the wall trying to see what you're doing. I've grown fond of number 6 as a way to test it. This is just a straight find the particular solution problem. No overlap, just the naive guess will work for this one. Problem 8 actually has overlap, so you have to multiply by t, right? So a lot of people got problem 8 wrong last year. Superposition. Here is net force, find the velocity as a function of position problem. So you got to use the v dv dx trick. M dv dt is v dv dx. Then you got separation of variables, integrate, off to the races. That might have been a homework problem for them. And then, Cauchy Euler, but that's out. This is actually interesting. This is a non-homogeneous Cauchy Euler problem. Wouldn't be terribly surprising if that was on your next quiz. Anyway, so you guys have a good week. I'll see you Thursday. So. Mm-hmm. I think you guys would be okay. I mean, we Tuesday, Thursday, right? I mean, I think it'll be okay. I mean, I can start 5 minutes early probably, and go 5 minutes late if that's helpful. Sure. I don't think there's anything pressing in here before and after, but probably just 5 on each end. Okay.
Can you explain this common? Because